Is the one of the first lake lectures when we're thinking about how lakes are formed, what different types of lake and what lakes there are, and where we find them. So, um, what is a lake? It's just basically a depression filled with water. Now, I don't necessarily want to talk about the difference between where's the line between a lake and a wetland or a lake and a pond. Let's just forget that right now. Um, Even though there like really isn't a good way to explain the difference between those two. But the first thing we want to talk about is tectonic lakes. Now, tectonic lakes are depressions that are formed because the Earth's crust is moving. Now, because the Earth's crust moves so slowly, and things just don't change that quickly. These are the oldest lakes on Earth. Okay, the first type of tectonic lake is called graben. Now, grabens are essentially what you have here is where the crust of the Earth is diverging. Okay, so when the crust here, these two plates, this is one plate, and here's another one that then are moving apart from each other. This dirt here basically just kind of falls down, and this then moves down. Lake Tahoe in Nevada and California is an example of this, but that's maybe one of the closest graben lakes. But the biggest one and the oldest lake in the world is Lake Baikal, which is right here in southern Russia, kind of north of Mongolia. Now, and then some of the African lakes are like this. So these lakes can be extremely old, extremely deep, because essentially they're like, ever deepening. So they don't ever fill up with sediment. So the crust is continuously pulling apart, making this continuously fall down. So you get, just an ever deepening lake that, at least on, any time scale that is almost imaginable, at least. And these lakes can be then millions of years old. Another type of tectonic lake is when crust gets warped. Okay, so just like when we have lakes pulling apart, or Earth's crust pulling apart, it can create a basin. If you press it together, so if you have a compressed force making one portion of the Earth's crust, it like crinkles together and you get a fold in it, and then this fills up with water, and then you get a nice lake there. Okay, so this can create basins like that. They can create dams in certain areas, cut off outlets. If a certain area had a stream, if there was a stream running through here going that way, but then once we get this folding, it basically cuts off that stream, and you can create get water like here. Lake Okeechobee in Florida, that big lake right here, that's an example of an upwarping lake. Lake Victoria in Africa is one of these. Great Salt Lake is an example of this. So if we, Great Salt Lake here is right here, right about there. Oops, sorry about that, bad drawing, in Utah. And basically it's like a big basin that with mountains all the way around it, and all the rivers just kind of flow into there. Now the Great Lakes are kind of like this. We'll talk about why here in a little bit, but I'll save that for here in a second. Next type of lakes are volcanic lakes. There's caldera lakes are really common. What happens here is in this little picture up here, you got an active volcano, right? The active volcano is going, and then once it becomes inactive, what happens is the magma that was underneath basically the whole volcano recedes for one reason or another. So basically you've got this like big, huge empty space that the ground can't hold up, and then you get the whole mountain to like collapse, and you can then get a big basin in there. this isolates that watershed. That with the lakes are oftentimes really, really nutrient poor because it's just like bare rock and really volcanic rock that doesn't have a lot of nutrients in it. So you can get these like high lakes, Crater Lake in Oregon, Yellowstone Lake in Yellowstone National Park is an example of a caldera lake. And then you can get all sorts of lakes caused by volcanoes due to volcanic dams. And, this is anytime you have a lava flow flowing down, you can get water filling up in certain areas and create, whole valleys that get cut off and turn into a lake then. Now, glacial lakes. Glacial lakes are the most common type of lake. Across the world, majority of lakes are caused from glaciers for one process or another. So what we see is basically every time here you get okay, what we've got here is years before present here, okay? And when we go 50,000 years, basically from 100,000 years ago to about 20,000 years ago or so, we had a big glacial period. Okay, and this is the Pleistocene ice sheets, right? What we have is here is a map looking at where glaciers were during that glacial period. All the white area was area that was covered in glaciers. So if we look at North America, right, basically all of Canada all the way down to, let's go back to this map now, all of Minnesota, most of Wisconsin. If you look, there's the southwestern Wisconsin had this area called the driftless area for reasons that I forget at the moment why we didn't have glaciers there, but all of pretty much this Wisconsinian glacial period, which is, that 100,000 years ago to 20,000 years ago, is this kind of like this tan area right there, right? And what we see is when you look at all of the lakes, like in northern Wisconsin, so this is a picture of northern Wisconsin, and, all these different lakes that are dotted all across the landscape right here are due to the glaciers. Now, how do these happen? How does a glacier form a lake? Well, the first thing is, think about a montane glacier at the head of the glacier. So what happens is, the snow piles up in the river valley all along here and starts to fall down and starts the start of a glacier. And what oftentimes this does is it makes this big pool kind of at the top, and you can see if this glacier were to melt, there would become a cirque lake right there. But the combining ice flows then come together and create what we call a cirque. And again, these lakes are really oftentimes very cold because they're high altitude, mostly just rock that doesn't have very many nutrients in it. So, and there's very few fish because, how does a fish swim up a mountain to get into this area, right? So, very interesting types of lakes, but biologically, not much really going on in them. Now, the next type of lake is glacial scour lakes. So think about a huge sheet of ice that is moving. Okay, these can be valley glaciers, but they can also be the continental size glaciers that we were talking about with that Wisconsinian period of glaciation. This is where the Great Lakes come from. Part of the reason why we have the Great Lakes. So the Great Lakes were caused by the Laurentian ice sheet. So if we think about this big ice sheet that was moving from Canada down, it was 2 miles thick and it was moving. So it's basically like a giant bulldozer that scraped out Lake Superior, Lake Michigan, Huron, Erie. And this is labeled incorrectly. I pulled this just off of Google Maps. That's interesting. That's Lake Ontario. Not sure why that is. Lake Champlain is actually just a tiny little lake in between Erie and Ontario. Anyway, just realized that. Sorry. So, The thing is, though, the Great Lakes are caused by a different reason too, and that has to do with or the glaciers warping the crust of the Earth. Okay, so imagine like a basketball, and then you press down. Take your fingers, grab the basketball, and press down with like your two middle fingers when they're close to each other. What that does is it kind of creates a depression in the basketball, right? And that's what happened with this 2-mile thick sheet of ice, which basically was a ton of weight on the crust that pushed it down. And even though the ice went away 20,000 years ago, what we're still seeing is that the crust is still rebounding. Okay, so there was 80-some thousand years of ice, weighing down on that portion. And I should maybe go to this thing, right? So, we have this big amount of weight basically pressing down in this area. And what we see is there was this whole region is rebounding now, and Hudson Bay, which is this area of water, and the Great Lakes are actually getting shallower, and their crust is rebounding. And what we see is, up the farther north you go, the faster it rebounds, just because it was, weighed down more with ice, where this is kind of the edge of the ice, right? But, the northern part of Lake Superior is rebounding at 21 inches per century. And then, Lake Michigan part of it is at 3 inches per century. So it's what's the Hudson Bay is essentially, in, I forget how many tens of thousands of years, but Hudson Bay should essentially completely go away as the crust rebounds and there's no longer that depression there. And the Great Lakes then will also do that. So the smaller type of lakes that we see are kettle lakes, okay? And think about that big Laurentian ice sheet coming over, being on top of Wisconsin, okay? Then what happens is the glacier retreats. It doesn't actually move back, but it just starts to melt, right? And essentially what happens is that big giant ice blocks get, just trapped in areas, okay? So we got these big giant ice blocks. And because this glacier then is continuously melting, what you see is it's melting and then the water runs off and we get this outwash of dirt filling in around these areas. So what happens then is, over thousands of years, this ice block melts and then we get a kettle lake. And these are all the smaller, irregularly shaped sized lakes that we have in basically northern Wisconsin, or just pretty much any lake around here, really. The thing is, these aren't super deep. These blocks are not more than 50 meters, 150 feet deep, so you can't get super huge lakes out of this type of lake formation. There's a variety of other types of lakes, solution lakes. So think about a sinkhole. If what happens is if you have limestone and water infiltrating into limestone, making a cave, and then this area collapses down to create a basin. That's essentially this sinkhole. Think about over time, essentially this basin would fill up with water and create a little lake there. Sorry, that came up. Wind formed lakes, so oftentimes like sand can get blown around and blow out some area and create a basin. Rivers themselves create oxbows. So this is a river that's flowing right here, and what we see is the river used to flow in here, okay? And so like where the river used to be is just a small short-term lake that will be there. These are called oxbows. If you're from Australia, they're called billabongs. Then there's plenty of floodplain lakes, right? Like if there's a little basin in here, if this lake floods and fills it with water, it can have lake for a short amount of time. There's lakes of organic origin, so reservoirs that people create, beaver dams, and they make a little reservoir. Aquatic plants can like dam up stuff and create lakes sometimes. And then, if a asteroid hits the Earth, this is one of the biggest lakes meteor-created lakes. It's kind of weirdly shaped, but it's in, I think it's in Quebec, northern Canada, and you can see it's relatively circular in shape because that's the asteroid that hit, somewhere in here and creates a crater. So there's lots of other ways to, create lakes, but these are basically all the main types. But I'd want you to concentrate on the glacial types because those are the most important, most common, whereas these other ones happen but aren't necessarily as common. So, I'd like you to think about this question. Which is older, Mississippi River or Lake Superior? So when you think about this, you think, well, Lake Superior is huge, been around a long time, yes. But what about the Mississippi River? And the answer is, lakes are actually, if they're not tectonically formed, they're really ephemeral. They're really temporary, right? So the average glacial lake, how old it is simply just since the last time it was covered over by a glacier, right? So if we go back to this, interglacial period, we are in, this interglacial period where we have no glaciers. But the last time we had no glaciers was, this time frame. And really for most of time, most of, the recent past, recent meaning, what is this? 450,000 years. We're lucky that we're living in this interglacial period where there are not, half the world is not covered in ice at this point. So the thing about this though is, this glacial period right here. Well, so let's say there was a bunch of lakes, created in this glacial period that appeared, in this interglacial period. Well, it's essentially like the bulldozer came again and completely flattened out and made all new lakes right here. Okay, so the average glacial lake is really only as old as at max, like this 20,000 year old at max. Whereas Lake Baikal is like 30 million years old. It's been, been there forever. Lake Malawi is several million years old. Lake Tanganyika, 9 to 12 million years old. So all these lakes that are tectonically created are very old, but glacial lakes are really young. And also, the glacial lakes, being that they're relatively small and they're not ever deepening like Lake Baikal is, they fill up with sediments, right? You have algae growing in here. You have rivers flowing into here, putting sediments in here. You have just dirt blowing into it, right? And all of that, all of what happens then is, even though a lake is, let's say, 150 feet deep, on geologic time frame, that's not that long. And eventually, the lake fills up with sediments and eventually can either just, fill up with sediment and become, dry land, or it can become some sort of bog where you get a bunch of moss that creates a weird type of wetland that we'll talk about towards the end of the semester. But, basically every lake will turn into, every lake, if it's not actively getting deepened, through geological processes, is going to fill up with sediment. On the other hand then, rivers are freaking old, right? Basically, how long has water been running off the continent somewhere in the Mississippi River Valley? And the answer is 200 million years, right? The Amazon is 200 million years ago old. It's changed directions, right? So 200 million years ago, South America was stuck up with Africa, right? And the river flowed to the west. But since then, South America broke off from Africa and the Andes Mountains arose, we see then the river changed directions and now flows to the east. So, these rivers basically change course, but so maybe the Mississippi River used to be over here. Well, that's fine, because just the fish that were living in here, or whatever was living in this lake or river over here, will just, kind of go along with the river. As the river changed course over to its present day course, those fish are just living there just fine. So the river is different, but it's still been there forever. All right, so let's change modes here and think about lake morphometry, okay, how a lake is shaped. Now, we need some definitions first, and that has to, so let's talk about the littoral zone versus the limnetic zone. The littoral zone is like the edge of a lake, the shallow area of the lake, and it's usually on the edges, right? But if you have an island or something, you know, like a seamount or whatever, well, I shouldn't say seamount, but think of like an island that is not all the way up to the top of a you know, not an island, but still just submerged a little bit. That could still be considered the littoral zone. And these areas are highly productive, right? The reason is because they have a variety of different habitats that can be used. So let's just think about primary production. You can have phytoplankton, just like you have phytoplankton out here, floating algae growing in the top of the water here. You'll have that here, but then you also have plants that can emerge from the water or be submerged and floating. So there's a variety of different niches that those plants can have and allow the productivity to be higher. Whereas out in the open water, essentially, you know, there's no plant that's going to be able to grow up out from, you know, in 30 feet of water. So this is just the algae alone. It's less productive, but there's still a lot of production going on there. So what we see is lake morphology is really tied to how the lake was formed. So, you know, a reservoir here, you have a dam here, is the water fills up and it fills and makes contours of the river valley, right? However that valley was, then you get really, you know, weirdly shaped lakes, whereas like a crater lake is really circular. This is Crater Lake in Oregon. So, you know, when we're looking at things like area and max and average depth, those are fine metrics to use, but one metric that is interesting is called the shoreline development ratio. Okay, and now what the SDR, shoreline development ratio, does is it's a ratio of the perimeter to the circumference of the circle with equal area. Okay, so what does that mean? Okay, think about well, hang on. What this ratio does, it varies from 1 to infinity. Okay, there's, you know, it's not going to be infinity, but, you know, theoretically it can be up. And what happens is, think about a lake that's essentially pretty circular. Okay, well, right here. Think about, you know, this circular lake, Lake C, versus let's call this Lake 1 and Lake 2. Okay, now Lake 1 is pretty much a circle, and essentially what it's saying here, well, is that this lake has the minimum amount of littoral zone, you know, assuming everything else equal depth and stuff. Because it's a circle, it has the minimum amount of shoreline, minimum amount of littoral zone. Whereas this lake, where that's really jagged and has all sorts of different shoreline, has more limnetic zone. So the larger the number, the more littoral zone and the more productive it will be. So what do you want to do? Here is how you find the shoreline development ratio. It's, first off, you need to find the perimeter of the lake. Okay, so that's P. Then you find the area of the lake. Then what you do, step 3, is use the area of a circle formula to find the radius of a circle with equal area to the lake. Okay, pi r squared equals the area of your, you know, normal lake. So then you find a theoretical circle that has the circumference of this theoretical circle, and then you use this equation of your shoreline development ratio equals the perimeter divided by that circumference of a circle with equal area. Okay, so this is confusing, so let's go through it. So let's say we have some sort of lake, I don't know, that looks like that. And let's say its perimeter equals 723 kilometers. Okay, so it's a pretty big lake. And its area is, let's say, 6,000 kilometers squared. Okay? Now, what you do is you take, now we found the perimeter of the lake and the area of the lake, right? Let's say we use ArcGIS to figure that out. Now, pi r squared equals, the area is 6,000. Okay, so r then equals the square root of 6,000 over pi, right? So the radius of this hypothetical lake is 43.7. Oh my gosh, that's terrible. 43.7 kilometers, right? Now we need to find the circle. So what this is saying is, if you were to have a circle of area 6,000 kilometers squared, so if you have some circle, and then if you were to have a perfect circle, the radius of a circle with 6,000 kilometers squared would be 43.7 kilometers. Okay, so now let's find this circumference, right? So circumference equals 2 pi r. So, you know, just 2 pi times 43.7. And that would then equal 274.59. Okay, so this theoretical circle with 6,000 kilometers squared would be 274.59 kilometers around, right? So now we then can figure this shoreline development ratio equals the 723 divided by the 274.59, and that equals 2.54. So sorry about this terrible writing, but I highly suggest you go through these calculations again and try to see if you can get this 2.54 number. Excuse me. So what does this 2.54 number tell us? The answer is the higher that number, the more or the less circular that lake is. So, you know, this would have a number, a shoreline development ratio of maybe something like 1.2, whereas something like this maybe would be 2, whereas something like, I don't know, some weird, you know, lake that's, let's say that there's a dam right here and, you know, something looking over like here, this would have a number of maybe 4 or 5 or something, right? And what that's going to mean is that this lake has more littoral zone, which can be productive. So the shoreline development ratio is a way to look at a lake and take some shortcuts and see how much littoral zone there is and how productive it can possibly be. So now let's look at another way to look at lake morphology, which is called a depth area curve, also known as a hypsographic curve. Okay, so what this does is it kind of like shows at each port depth how much of the lake is like at that depth. Okay, so let's say we have a lake like here, Lake A, which has these gently sloping banks, and then a small, you know, deeper portion that's not very big in area, right? You know, this is the cross section of the lake, you know, like we're looking at it from the side. So what we see here is what depth is this is the surface at, you know, 0 meters deep, and then this is the deepest portion of the lake. Okay, and what we have here is then, you know, here is that little plane that's right here, and then we show the gently sloping curves along that blue line, right? Now compare that with Lake B. Lake B, the cross section of this shows that there's a real wide, real big, deep plain there. That's with very steep banks or shorelines. So I mean, what this is really looking at then is there's essentially not a lot of area at 1 meter deep, right? There's only like this little portion here and this little portion over here on the right and the left that have 1 meter deep, and that's shown by this very steep curve over here, right? So compare this lake over here. What can we pull from this information or from this graph? What we can see is that the lake itself is about, let's say, 142,000 meters squared. Okay. What's its maximum depth? Maximum depth is over at 11. And what we can say about this lake is it has a deep hole, but it's a very small deep hole. And then it has like a broad plain kind of from 6 to 8 meters deep, and then like a little shallow littoral area, a decent amount of shallow littoral area, then it kind of goes down. So this gives you an idea of how much of the lake is at each depth. So how do you do one of these? So let's say we have this very unrealistic square looking lake, okay, and what we've done is, here's the shoreline of that lake. And we put it into a box, 20 boxes here, and we've measured how deep is the lake right here. It's 1 meter deep here. It's 2 meters deep here. It's 5 meters deep here. It's 7 meters deep. And generally what we think about the lake, it's, shallower around the edges. In the middle, it's deeper. There's differences here, and this is an unrealistic scenario. But what you then have to do is count up how much of the lake is at 1 meter deep, how much of the lake is at 2 meters deep, how much of the lake is at 3 meters deep, and so forth. So that's what I did over here. Okay, and it's best to start at the deepest point and go towards the shallow. So how many boxes are at 7 meters? 1. How many boxes are at 2 meters or 6 meters? 1, 2. Okay, so and so forth, right? Then you need to do a cumulative area thing. Okay, so so this starts at how much of the area is at basically 7 meters or deeper. Well, it's only 1 box. How much of the area is 6 meters or deeper? So it's just 1 plus 2 equals 3. How much of the lake is 5 meters or deeper? It's just 3 plus 4 equals 7. Okay, and you just add up and we get up to 20, just like this is a 5 by 4 box, right? So what we do is depth 0 to 7, okay? And then here the area is 0, I haven't done this, so this is 10, this is 20, so 2, 4, 6, oh, that's not very equidistant. Neither is that one, but kind of get what's going on here. Okay, so we have our depth of 7 meters down here, and then we use the cumulative area as our x-axis. So this will be our x-axis, and this will be our y-axis. So you got 7 and 1, so you put a dot right there. Then we've got 6 and 3, so maybe I should have. So that's 3, 4, 5, 6. I know this is riveting watching me make a graph here, but okay. So we'd go at 6 and then 3, and then we do 5 and at 7. 4 and 8. 3 and 11, 2 and 14, and then, 1 and 20, right? So then we go connect these lines. There. That is our hypsographic curve for this fictional lake, right? And you know, this again shows that there's like one hole, that's one small area that is relatively deep. But you know, there can be all sorts of different curves depending, let's go back here, depending on the whole shape of the lake will change this hypsographic curve. And if you have an island in the lake, you know, if there was, you know, an island up maybe somewhere in here, so this was, you know, not lake, that, you know, that would maybe make this portion of the graph look like longer out that way, or to have more shallow area. So yeah, what I would say is we're going to do an assignment on both of these things, so be prepared for that, and certainly ask me questions later on. All right, with that, I'll see you later.